Okay, so hello guys, I am going to be presenting the introduction to PROTOGALAXY. Okay. So Jern mentioned a lot of the things that I was going to cover. So like folding schemes started with NOVA, which was for R1CS. Then you had Supernova, which was multiple R1CS instances. For non-uniform IVC. For non-uniform IVC, I think this was covered by Flora. Okay, then you had Hypernova as well, but we're not interested in that. Then we had Protostar. So Protostar generalized the concept of folding schemes for stuff other than like R1CS or CCS constructions. So with Protostar, what you can do, I mean, this is stuff that was mentioned by Jern, that you can fold like arbitrary polynomial maps. So like any polynomial function. Yeah, so for example, we have R1CS, right? So R1CS is A of X, or wait, A Z dot PC CZ to 0 equal to CZ. You can write it as fx and a polynomial map, let's say fx. You can rewrite this as fx equal to ax vx minus cx 0. And yeah, like this is a vector equation, and like each of them would be like, if you want to write it as fi of x, it would be like a of like xi, p of xi, or axi bxi cx of y equal to 0. So like the R1CS instance is the combination of all these equations. So basically Protostar is like a more general scheme which can be used to express R1CS constructions like Nova and Supernova as well. And yeah, the reason why most of these folding schemes work, again this was covered by a lot of people, is because like you can create a commitment to this like this equation or this kind of polynomial map in which the commitment would hide all the like the witness value. So x here is the witness, right? So the commitment would like the verifier can verify or when you fold an instance of these equations, what the verifier can do, like he doesn't need the witness to fold all the other equations. He can just fold the commitments to the witness as well, and that can result in a new folded pair which can be used to verify like the combination of original witnesses. Okay, so this was like background, and yeah, PROTOGALAXY is an iteration on Protostar which can be used to PROTOGALAXY. Can fold multiple instances of Protostar. Makes sense, right? Multiple star galaxy. Okay. Now, so I'll express like the same thing in a like a diagram. So in Protostar, what you have is you'll have your running running instance, which would be like a commitment and a witness. So this is like the running instance. Witness is stuff that the prover has, and commitment is stuff that the verifier has. The prover has both, but the verifier doesn't have access to the witness. Then you'll have like your current witness pairs, like phi I, phi 1, omega 1, phi 2, W2, phi k, WK. So you have k instances, and what ProtoStar does is it folds all of this into a new witness pair, phi star, W star. So instead of just folding like one new instance at every recursive iteration, you're now folding k instances at once. And this is the main contribution of ProtoStar and ProtoGalaxy, and it does it like more efficiently. So yeah. So why is this difficult? Like, why can't you fold just k instances in like whatever you're trying to do in any simple method? Like I can try to give like a simple intuition. Like if you have any constraint which is of degree d, and you're trying to combine like k different values of it, plus k different instances, like then the degree of the cross terms that you will get, which we will depend on k, right? Because you will have like the combinations of all these terms. You will have x1, x2, x3 up to whatever xk minus 1 or whatever. So the degree of cross terms is exponential in k. So this will explode. Like if you're trying to combine 3 or 4 terms together, because it's exponential in k, the number of cross terms will be too large. So yeah, you won't be able to efficiently do this. So what ProtoStar does is when it's folding like these k instances together, instead of just using like a random linear combination of the, like all of this stuff, what it uses is that it takes all these witness pairs, like all the witness pairs, and it uses like Lagrange coefficients as the stuff that it uses to combine all these witnesses. So I think you guys had a session on Lagrange polynomials, right? So Lagrange polynomials, I can give like a very short overview, but let's say you have like a number n. You're working in with nth. Let me actually say this. So uses Lagrange polys to combine. Lagrange polynomials. Actually, I'll remove this. Galaxy. Lagrange polynomials or Lagrange bases. So Lagrange base. Let's say omega is the nth root of unity. Root of unity. That is omega power n equal to 1. Like in the prime field, and you have H, which is a set of all the roots of unity. Then the Lagrange basis is this kind of polynomial in, let me write it as x. Oh wait, no, this is fine. J. Yeah, so the Lagrange base is only equal to 1 if you're looking at a particular coefficient or a particular power of like this root of unity. Otherwise, all the other values, the Lagrange base would be 0. So what Lagrange bases do, like if you're trying to combine things using Lagrange bases, you can see that it's creating some kind of separation between all of the terms, right? Like if you use some particular type of math and you do like operations on some particular kind, then because the coefficients are Lagrange bases when you're combining all these instances in PROTOGALAXY, you can combine them in a way in which the degree of the cross terms don't explode. Like you can combine it in a way in like some of the Lagrange polynomials are 1, others are 0, so the only terms that you get are still low degree. I'm not going to explain how exactly that is done, maybe next week, but yeah, that is the there's still some left. but that is like the kind of intuition behind PROTOGALAXY on how it can combine like k different instances into one instance using Lagrange bases. So when you're combining these, right, these instances, like the coefficients that they would be kind of multiplied by would be Lagrange bases. And there are some other stuff as well, but like I can write down the equations, but I don't understand the equations, so I don't think they are relevant. Let me see if there is anything left.
So that means the key takeaway is that PROTOGALAXY is something like a folding of protostars, and the trick is that you kind of need to combine the cross terms using some Lagrange bases, and some magic will happen for the cross terms to not explode.
Exactly, and you can combine like instead of combining 2, you can combine like 5 at a step, and the number of cross terms will not explode.
Does it make it faster than because everything is like just like there and this is fold like 2 at a time, right? But now say it's like 5. Would that make it like shorter, faster, or what?
I think it will make it faster, yeah.
But the prover has to do a log and computation, but in ProStar there's no such thing. So it will be not easy to compare them. But ProStar kind of more elegant. ProGalaxy more elegant.
Yeah, I'm not sure if it's more elegant, but I can tell you like this kind of folding. Like there are 2 different kinds of way in which like PROTOGALAXY is constructed. In one, the prover complexity is order of I think k log k, and verifier is order of k. This is like the normal way. Let me check. Yeah. Like if you want to read the paper, then this is like section 4 of the paper. There's also section 5 in which they optimize it, in which I think prover becomes order k. Order of k, verifier is order of log k. This uses sum check, but the constants here are bad, so like you'll have to do actual benchmarking to see if this makes it much better or not. But yeah, the actual PROTOGALAXY protocol I think we'll discuss next week when I understand more of it.
Thank you.